When going through optimization problems, we'll be working with continuous, smooth, differentiable functions that have a maximum and or minimum value in the relevant interval of x. That just means that we can find a derivative at every point along the curve. Common functions that we'll be looking at look like this: our quadratic functions and our cubic functions. Let's go through some of the basic terminology. Single variable optimization of a function y equals f of x is the process of finding the value of x that results in the best value for y equals f of x. And best can be defined as either a maximum, which is the value of x that yields the highest value of y equals f of x, for example, if I'm choosing output to maximize profit, or best can be defined as a minimum, the value of x that yields the lowest value of y equals f of x. For example, a firm choosing output to minimize average total costs. So let's look at maximization and minimization on a graph very briefly. Maximization is a process of finding the maximum, the value of x that yields the highest value of y equals f of x. So on this little sketch here of this graph, and you'll never see functions that look like this in this class, but we would find maxima here at a, d, and g. And minimization is the process of finding the value of x that yields the lowest value of the function y equals f of x. So on this graph, we have minimum values at b, f, and h. Now, to study maximization and minimization problems, it's important to know what a stationary point is. The stationary point of a function is also known as its extrema or its critical point, is defined in three ways. First, the verbal definition. The stationary point is the value of x such that the function is neither increasing nor decreasing. The mathematical definition is that the stationary point is the value of x, we call it x star, that solves dy dx or f prime x equals 0. And the geometric definition is that the stationary point is the value of x such that the slope of the tangent line at x is equal to 0. Let's look at that graph of that crazy function again. The stationary points of f of x are labeled as a through h. At every one of these labeled points, the first derivative of the function is 0. In other words, f prime x equals 0. That slope of the tangent line at a, b, c, d, e, f, g, and h are all 0. So how can we classify whether a stationary point is a maxima like in a, d, and g, a minima like in b, f, h, or an inflection point like c and e, if at every stationary point the derivative is equal to 0? Well, there are two main classification systems for identifying maxima and minima. The first one is called the first derivatives test, and it makes use of the first derivative only by comparing slopes around the stationary point. And then there's the second derivatives test. It makes use of both the first and second derivatives by identifying the curvature of the function around the stationary point. So the first and second derivatives test both are telling us the same thing. They yield the same results, but they just tell us or yield the same results in different ways. What you need to know for this course is the second derivatives test. We'll still go through the first derivatives test just for intuition. Now some more terminology. We've been working thus far with the first order derivative, or just the first derivative. And that first derivative tells us the rate of change of the function f of x. And it's denoted as either dy dx, or df of x over dx, or f prime x. Every single one of these tells us how the function changes with respect to x. And what it really does is this first derivative tells us for what values of x the function is increasing, decreasing, or constant. And we can summarize this mathematically. So reading across the rows, if f prime of x is greater than 0 on some interval of x, then we know that the function is increasing in the interval. If f prime x is less than 0 on some interval of x, then we know that the function is decreasing on the interval. And if f prime x equals 0, then on some interval of x, then the function is constant. Now, we're going to introduce the second derivative, or the second order derivative, which tells us the rate of change of the first derivative f prime x. In other words, it's telling us the rate of change of the rate of change. And it's denoted as d2y over dx2, or d2f of x over dx2, or f double prime x. I'll be using the double prime from now on. Keep in mind, these 2's don't mean squares. It's not saying d squared y over dx squared. We see notation like this in terms of calculus. All this means is that you're taking the second derivative of the function f of x with respect to x twice. Now graphically, what the second order derivative tells us is for what values of x the function f of x is bending upwards, bending downwards, or neither. So in mathematical notation, we can write the graphical interpretation of the second derivative as follows. So reading across the rows, if f double prime x is greater than 0 on some interval of x, then the function f of x is bending upwards in the interval. It's like a smiley face. If f double prime x is less than 0 on some interval of x, then the function f of x is bending downwards in the interval, like a frown. And if f double prime x is equal to 0 on some interval of x, then f of x is a constant. So let's take a look at the concave upwards and concave downwards definitions. Concave upwards just means bending upwards. So if f double prime x is greater than 0 on some interval of x, then f of x is bending upwards. We just said that. For example, if y is equal to x squared, then the first derivative f prime x is equal to 2x, which is negative or downward sloping for x less than 0, and is positive or upward sloping for x is greater than 0. F double prime of x equals 2 for all values of x, whether x is negative 10 or negative 3 or 0. This function is bending upwards. And we can graph this out. Here's a function, or here's a graph of the function f of x equals x squared. Now concave downwards just means bending downwards. Concave downwards is defined as f double prime x is less than 0 on some interval of x. For example, if y is equal to negative x squared, then f prime x, the first derivative, is negative 2x, which is negative or downward sloping for x greater than 0, and is positive or upward sloping for x less than 0. And taking the second derivative, f double prime x, we get negative 2, which is less than 0 for all values of x. In other words, this function is always bending downwards, like an upside down frown. And we see that when we graph it. Now, before we go through a maximum versus a minimum, I'd just like to summarize the second derivatives test right away. You'll see this table later on. So the second derivatives test is just one set of conditions used to find and classify maxima and minima of a differentiable function. So there's basically two things that you need to look at. The first is the first derivative, or that first order condition. And then the second derivative is the second order condition. The first derivative is going to be the same whether we're looking for a maximum or a minimum. The second derivative is what's going to allow us to classify whether that point is a maximum or a minimum. So for a maximum to exist, a maximum value some x star, the first derivative at x star equals 0. And then the second derivative at x star is less than 0. So the function bends downwards at x star. Think of that top of the hill. For a minimum, the first derivative is going to equal 0. And then the second derivative is at x star has got to be greater than 0, which means that at x star, the function starts to curve upwards. So think of the bottom of a valley. In some instances, you're not going to be able to use the second derivatives test to classify. For example, you may find that the first derivative is equal to 0, but that the second derivative is also equal to 0. We're not going to come across instances like this in this course, and in most of your econ courses, you won't come across this either. We're going to focus on maximum and minimum. So let's begin with understanding maxima. Finding a maximum value, or maxima, or the stationary point at the top of the hill. So first I want to talk about the first derivatives test because I think that's intuitive, and I want to then talk about the second derivatives test for finding a maxima. So for the first derivatives test, at a maxima, the first derivative is 0. We know that. The first derivative is positive right before the maxima and is negative right after the maxima. So what does this mean? At a maxima, the stationary point, right? We're first finding a stationary point. That derivative is equal to 0. So here it's at x sub 0. So at x sub 0, the derivative equals 0. Now, the derivative right before x sub 0 is greater than 0. We're going up the mountain or up the hill prior to reaching the top. And then, after we reach the top, we start to go down the hill so that the derivative right after the x sub 0 is actually negative. Now, instead of looking or just using first derivatives, we can more simply say that the curve, or we could simply determine whether the curve bends downwards, i.e. is concave downwards, at x sub 0. Which just means, again, that the second derivative should be negative at x sub 0. So, using the second derivatives test, we would first find the stationary point by setting the first derivative equal to 0 and solving for some x, in this case x sub 0. And then we would find the second derivative, and we would ensure that it's a maximum so long as the second derivative is less than 0 at that point. So for example, let's find the stationary point of the function and verify that it's a maximum using the second derivative. So here's the function y is equal to negative x squared plus 4x plus 5. So here are the questions or the steps that we're going to follow. First, we're going to specify the first derivative and set it equal to 0. That's that first order condition. And then we're going to solve for x. We're going to call this outcome x star. Then we're going to evaluate the function at x star to find y star. Then we're going to specify the second derivative. If the second derivative at x star is less than 0, then we can say that x star is a maximum. If the second derivative at x star is greater than 0, then x star is a minimum. So with this function, let's go through step 1 first. The first derivative is negative 2x plus 4, and then I'm going to set that equal to 0. I solve for x and I get x star equals 2. Then I evaluate the function at x star, and I find that y star is equal to negative 2 squared plus 4 times 2 plus 5, which gives me 9. Now I need to make sure that this x star is indeed a maximum. So I take the second derivative, that's just the derivative of the first derivative, and I get negative 2, which is less than 0 for all x. So I can say that yes, this is definitely a maximum according to the second derivatives test. Keep in mind, what matters for a maximum is that the second derivative is negative at x star. In this case, with this particular function, the second derivative is negative for all x, so we're good to go. Quiz yourself. Find the stationary point of the function and verify it as a maximum using the second derivative. The function is y is equal to negative 2x squared plus 16x plus 100. Here are the steps to use. Specify the first derivative, set it equal to 0. Solve for x, call it x star. Evaluate the function at x star to find y star, and then specify the second derivative. Using the second derivatives test, we know that if the second derivative at x star is less than 0, then x star is a maximum. That curve is bending downwards at x star. But if f double prime, or the second derivative of x star, is greater than 0, then we know that x star is a minimum. In other words, at x star, the curve is bending upwards. So pause the video and try this on your own. So the first derivative is negative 4x plus 16. I set that equal to 0. I solve for x and I come up with a stationary point of x star equals 4. I plug that value into the function. I evaluate the function at x star and I yield y star is equal to 132. The second derivative is negative 4. The second derivative is just the derivative of the first derivative. And negative 4 is less than 0 for all and every single x, so I do indeed have a maximum. Okay, so now let's move on to the minima, or the bottom of the valley. Again, I'll go through the first derivatives test first, because that tends to be the most intuitive, and then we'll talk about the second derivatives. So at a minimum, the first derivative is 0, the first derivative is negative right before the minima, and is positive right after the minima. So in math notation, the first derivative is 0 at the minimum point. That's the stationary point, x sub 0. And then as we're approaching x sub 0 from the left, the derivative is negative. And as we're leaving x sub 0, as we move along the x-axis, the derivative is positive. Now, instead of using just the first derivatives, what we want to use is the second derivative. Simply, what we're trying to find out is whether or not the curve bends upwards or concave upwards at that x sub 0, which is just asking, is the second derivative positive? So using the second derivatives test, what we're doing is we're setting the first derivative equal to 0 and solving for this x sub 0, and then we're trying to figure out if the second derivative is greater than 0 at x sub 0. And in this graph, the second derivative is greater than 0 for all x. For example, let's find the stationary point of the function below and verify it as a minima using the second derivative. Y is equal to x squared minus 4x plus 5. We're going to use the same exact 3 steps that we did before. We're going to specify that first derivative, set it equal to 0, and solve for x, call it x star. Then we're going to evaluate the function at x star to find y star. Then we're going to specify the second derivative, and using the second derivatives test, if f double prime x star is less than 0, then we can conclude that x star is a maximum. If f double prime evaluated x star is greater than 0, then we can conclude that x star is a minimum. So the first derivative of this function is 2x minus 4. Then I'm going to set it equal to 0, and I solve for x. I get x star equals 2. I'm going to evaluate f of x at 2, which yields y star equal to 1. And then I'm going to take the second derivative, which is just the derivative of the first derivative, and I get that f double prime is equal to 2, which is greater than 0 for all x. So, again, what matters for a minimum is that the second derivative is positive at x star. Since the second derivative is positive for all x, then we're good. This is indeed a minimum. Quiz yourself. Find the stationary point of the given function and verify it as a minimum using the second derivative. The function is y is equal to 4x squared minus 16x plus 40. Follow these steps. Pause the video and try this on your own. So the first thing I'm going to do is set that first derivative equal to 0 and solve for x. The first derivative is 8x minus 16. I set it equal to 0 and I solve for x, yielding x star equals 2. Then I evaluate the function x star to find my y star. Evaluating f of x at x star equals 2 yields y star equals 24. Then, just to verify that this is a minimum, or to even classify whether this is a minimum or a maximum, I'm going to specify the second derivative, which is equal to 8. I'm going to specify the second derivative, which is equal to 8. Remember, the second derivative is just the derivative of the first derivative, and that's greater than 0 for all x, so I do indeed have a minimum. So just as an aside, I want to talk about inflection points very briefly. This isn't something that you need to know for this course, but at an inflection point, the first derivative is 0, just like it is at a maxima or minima. But at an inflection point, the first derivatives on either side of that inflection point are either both positive or both negative. So consider the first graph, or the top graph. At this random point, x sub 0, the first derivative is equal to 0. It's a stationary point. But look at the derivatives right before x sub 0, that's positive, and right after x sub 0. They're both positive. So this is neither a maxima nor a minima. It's an inflection point. And we can follow the same sort of procedure for looking at this graph below. At x sub 0, we have a stationary point, so the first derivative is equal to 0, but check out the derivative right before x sub 0 and right after x sub 0. So right before x sub 0, the derivative is negative, and right after x sub 0, the derivative is negative again. So again, inflection points, we neither have a maxima or minima. We won't deal with inflection points in this course, but they're still important to understand that they do exist. So again, in economics, we are concerned with maxima and minima. Apart from sketching functions, inflection points are of little value. Now, in most instances, you're given a function and you're asked to find the stationary points and then classify whether they are maxima or minima. In the previous examples, I've given you a function. I've asked you to verify if it's a maximum or minima. But when you're asked to find stationary points and then classify, just use the second derivatives test. So again, to determine and classify stationary points of a function f of x, first, specify the first derivative of the function, set it equal to 0, and solve for x. Call this outcome x star. Evaluate f of x at x star. Call this outcome y star. And finally, specify that second derivative, which is the derivative of the first derivative, and use the table below to classify whether the stationary point is a maximum, minimum, or if it's just not classifiable. Examples. Let's find the stationary points of each of the following functions. Determine whether the stationary point is a maximum, minimum, or unclassifiable. We're not going to sketch these functions. We're just going to use math to determine the outcomes. All right, so we're asked to determine and classify the stationary points of each of the following functions. So let's just start with the first one. I'm going to follow these steps, 1, 2, and 3. So let's start with the first one, number 1. All right, so we got f of x is equal to 10x minus x squared. So the first thing I'm going to do is I'm going to specify the first derivative of the function. So the derivative of this guy with respect to x is 10 minus 2x. So this tells me the derivative at any point along the function, 10x minus x squared, but I want to find that stationary point. I want to find that point where the derivative is 0. So I'm just going to set that guy equal to 0. And then I'm going to solve for x. And I come out with x star is equal to 5. And then my second step is to evaluate f of x at x star, call this y star. So in other words, I just want to find the ordered pair, the other part of the ordered pair that's related to x. So y star is just going to be the value of the function evaluated at x star. So it's just going to be 10 times 5 minus 5 squared. Let's put that in parentheses. And so we get 50 minus 25, which yields 25. So y star equals 25. And then finally, the third, specify the second derivative of the function. So the second derivative is the derivative of the first function. So f prime x is just equal to negative 2. And I see that this is less than 0 for all. This upside down a means for all. So it's for all x. So no matter what value of x, no matter where we are along the curve, this tells me that the curve, bends downwards. At all x, including x star. So x star is a maximum. X star is a maximum. So if you wanted to, what I'm really doing right now, what I just found out is that I know that this is a form of a quadratic equation. What I'm doing is I just found this. I just found this point right here. I set the derivative equal to 0 and I came up with some, I can write this out if we want. This is just a rough sketch, obviously. Here's x, here's y. We just came up with some 5. That's my x star. I evaluated it at the function. And I got 25. All right, so let's move on to the next one. I'm going to clear this information out so that I can still have this available to me. So let's clear the page. Let's go on to the second one. So I have the function is negative 10x plus x squared plus 30. So the first thing I'm going to do is specify the first derivative. Negative 10 plus 2x. I'm going to set that guy equal to 0. Solve for x. I get x star is equal to 5. Then I'm going to evaluate the function. To find my y star is just the value of the function when evaluated at x star. and I get negative 10 times 5 plus 5 squared plus 30, and that should yield negative 50 plus 25 plus 30, so that yields 5, positive 5. There we go. And then I want to see, what is this? Is this maximum or a minimum? At this point, I don't know if I found something here, or I don't know if I found something like this. I'm not sure. Both of these are stationary points. All right, so let's go ahead and delete. Okay, cool. So for the third, I'm going to specify the second derivative. So the derivative of the first derivative is just 2, and that's greater for all, it's greater than 0. It's positive for all x, which tells me that x star is a minimum. In other words, at x star, the function is bending upwards, like this. There we go. So I'm going to clear this out now. And then we're going to go to the third one. So I'm going to set the first derivative. I'm going to set the first derivative of this equal to q. So what I'm doing is, my dependent variable, the y, is total cost, and the independent variable x is my q. So I'm taking the derivative of total cost with respect to q, which is just marginal cost. So I'm actually going to write that down. So marginal cost is the derivative of total cost, and I get 12q squared plus 12q minus 24. I'm going to set that equal to 0. And when I solve for q, and I'll do this, I'll divide everything by 12. I get q squared plus q minus 2 equals 0. You can use the quadratic formula, or you can factor it, whatever's easiest for you. But what you end up getting is a q star equal to either a negative 2 or a positive 1. But you're told that q is greater than 0. You can't have negative quantities of goods. So this isn't an economic solution. So we have q star is equal to 1. This is the relevant one. Negative 2 is certainly a mathematical solution, but we're just going to focus on the economic solution. So then I'm going to plug this guy into total cost. I'm going to evaluate the function. So TC star is total cost evaluated at q star, which is going to be 4 times 1 plus 6 times 1 minus 24 plus 50, which is going to be 10 minus 24 is negative 14 plus 50, so we get 36. And then finally, is this a max or min? I'm going to take the second derivative, so I'm going to take marginal cost prime q, which is the same thing as taking the second derivative of q, and I get, I get 24 q plus 12. So this one's a little tricky. So if this is a minimum, what needs to happen is, here, I'm going to break this apart. I'm going to say for a minimum, the second derivative has got to be greater than 0. So if q star is a min, then it must be that 24q plus 12 is greater than 0. So when I rearrange this, I get that this is true for all quantity greater than negative 1/2. So I don't even have to figure out the max. So I know that we're only focusing on the range of q is greater than 0. So if q star is equal to 1, that's greater than a negative 1/2. So I know that this is a minimum. Quiz yourself. Find the stationary point or points of the following cubic total cost function, assuming q is greater than or equal to 0. Determine whether the stationary point is a maximum, a minimum, or unclassifiable. Total cost function depends on q. It's equal to 2q to the third plus 3 times q squared minus 12q plus 20. Pause the video and try this on your own. So what you should end up getting is a q star equal to 1. And since the second derivative of total cost is greater than 0 for all q greater than a negative half, we're only concerned with q greater than a half, then we indeed have a minimum at q star equals 1.